so in the previous question, we deal with the particle, right? Which was a dense charge in some location, right? And right now we want to see how objects make forces and electric fields, right? So not long ago, I see an article about that bees, insects can sense electrical field. And this is the way they actually know where are the flowers, okay? So that's what we're going to do. So we have here a flower, a really nice flower, and this flower makes an electric field. Actually, I should do it with green, right? This is a flower, okay? Flower with the leaf, right? Here it is, really nice flower. And this flower actually have a positive charge on top of it. In which way this positive charge is distributed, as we did in the previous tutorial. Right now what I'm doing, I mesh up what we learn now and with the previous tutorial. This is the concept, the charge. So the charge is distributed really nicely. It's a constant which is positive all the time, multiplied by r squared. What does it mean? Where is the charge is mostly located? At the edges, right? Exactly, at the end. And the radius of this one is actually capital R, okay? And above the flower, in the middle, at location B, okay, we have a B, okay? So we have here a B, just think, right? Stripes. This is our nice B, okay? And we want to know what is the contribution of a small charge, only let's say this specific charge. How does this charge affect the B? Okay, understood what I want to do? I actually ask you first, okay? The first question, what is the magnitude of DEB from the charge? Only this one. Okay, and this is going to be at radius R. Okay, so what is this equal to? The equation for electric field. First of all, we have K, right? And secondly, we have the charge. What is the charge here?
The sigma times area.
Okay, this is a little advanced. Let's do it step by step. It's a small chunk of charge. I don't know what is it. We're going to solve this later. Okay, and what is the distance between them? So this is h and this is r, so this distance is? Yes, it's, let's call it d for simplicity, but it's actually h squared plus r squared, right? Great, so divided by d squared, okay? Note that there's two ways, this is the formula that maybe you're more familiar from high school, right? So electric field can be right as a K charge divided by the distance square and the direction R, right? It can be right as that way, but I also can multiply the vector R and R, the magnitude of R, both denominator and numerator, right? And then I'm going to have what we had before, KQ divided by the side to the 3, because this is just the size, and magnitude, the direction, what gives me? The vector R, right? So just a quick notation about that. So there's two ways to write the electric field vector. Okay, good. So we know that, so now let's develop it as you said before. Yeah, let's do it more explicitly. So we already talked about D, the distance, and note that I really love to put here D, not R, okay? Because sometimes we have a polar coordinates, and we're gonna already have R, so D as distance, it's a better notation in my opinion. Okay, so DEB is equal to K, and right now we need to figure out what is this. So what is this term?
The sigma times
Yeah, it's the charge. I remember you, what are the units of this? This is charge, right? Divided by meter squared. This is charge density of 2D plane, okay? K, good. And here we're gonna write sigma, but we need to fix the units. So we need to multiply by some area. What is this area? Gonna be since the flower look like this, yeah, right? I can look at the area that have length dr, yes, and have the other one, this thing, to be r d theta, right? Remember this one from the previous tutorial? So we're going to apply that. So here is dr multiplied by r d theta, and look that everything that contributes to the electric field actually depends on r. We see it, but it's not only depending in this way, it's also depending down there, because here we're going to have h squared plus r squared. You see it? We found it. We know what is the contribution from a really small charged particle on the flower. Yes? Good. So the second thing I want to ask you, vectors, we can talk about magnitude, and also we can talk about directions. Right, correct. So what is the direction, okay, of the electric field? Okay, what is the direction? That's going to be question 2, section B, right? What is, let's do it like this, E, B, direction, okay? And now I want to show you something, and I want you to be really careful, and this is really, really important, okay? Also for this subject, also for the homework, and also for the next subject, okay? I want you to see this thing. This is the flower, okay? Note, really careful. I want you to be focused. This is the B, right? This is the B. Here there's a positive charge, right? So this positive charge gonna produce electric field. In which direction? Radially out, outside of me. I don't want it, I don't want it, I don't want it. Specifically, in this direction. You see it? Good, okay. Now I want you to note, for every positive charge in some angle theta, I don't care about, there's another charge looking and laughing at me at that direction, 180 degrees, right? There's here a charge, right? Another one. And he's gonna hate the electric field and throw it away. Also in this direction, you're gonna throw it away. So what's gonna happen is if I'm gonna, project this vector in that direction, and project that vector in that direction, and in that direction, and also this one is projected in that direction, what are you going to see? These two cancel out, and these two sum up. So, and this is applied to every single charge. If this is the flower, if this is the flower, this is a couple of charges, this is, and for each distance, it doesn't matter. It's going to happen in every radius that you're going to choose, right? From 0 to capital R. Do you understand what's going on here? No matter what's going to happen, because of the symmetry, important word, symmetry of the problem, the electric field is going to point eventually only upwards. So I know that when the bees actually feel only electric field in that direction, she said, ha, got it. The flower, I'm on the top of the flower in the middle of the circle. That's what the bee understand, okay? That's the mechanism that bees and other insects know how to land on the flowers. Good. So what I can write is this. We know that the electric field is a vector, right? That the bee field, right, have some magnitude. I don't care what is the magnitude, but it has 0 contribution at x, 0 contribution in y, and a big contribution at z. All the magnitude actually lives in z when I actually note this is a z. Right? Good. So we have the direction, but we still don't know what is the magnitude of the vector, right? So the last thing we need to do is to find what is the magnitude. So question 2c. What is actually the vector EB looks like? Okay? Good. So I want to remind you, so the whole equal to what? The whole equal to the sum of its parts. We talked about when we talked about charge, but it's also true for vectors, because the electric field is actually comprised from the small contribution of charge. So this is actually built up from this thing, right? If I'm going to sum them all, I'm going to have the electric field. Agreed? Good. But we are smarter than that. We know something. We know that this does not exist, right? We know there's only contribution in which direction? Only at z direction. I know that I'm going to have y contribution. I know that this one going to give me that. I know that. But I also know that this one going to give me that. So I don't really care about it. They're here, they're alive, they're there, but they're going to eat each other up, okay? So that's what I want you to do at the homework. I want you to look at the symmetry and ask yourself, wait a minute, where is the charge cancelling? Otherwise, it's going to be a really hard problem. Because right now I need to solve only that, okay? It's not that I need to solve that. Do you feel me? This is pain in the ass, okay? I know this dying out, only need to find that one. Got it? What is actually dEz? What is its magnitude? Let's look here. Let's do that, okay? Let's clean that. So, if we're looking at the problem, this is the problem, right? This is the B, okay? This is a random piece of charge that produces this dA, which we know its value, right? We know it, we found it in the first section of the question, yes? But what is actually here, this tilt? I only care about dEz, right? So what is this magnitude? It's a projection of this vector, right? All I need to do, the only thing I need to do is to find the angle, this specific angle, right? Because this angle is actually this one, right? So I know that dz is actually dE, but a projection of it. It's sinus phi. You see it? See the geometrical problem? Okay? The one who solved the warm-up, this is what I gave you in the warm-up to do, in the Moodle, right? Okay? Or the one that have the book, this was also in the warm-up. Okay, so what is the size of sinus phi? Do you know what the size of it?
H over D.
We know that this is D. We know that this is H, right? So it's H over D. What I see in front of me divided by the long one of the, so dE divided by the ratio H divided by D. So look that I'm losing some of dA, right? Because D always gonna be longer than H, this ratio. This is fixed ratio, right? That canceling this out. Good. So, sorry, I said it's fixed. It's not fixed because D dependent on R, right? Big distance, it's gonna be longer, okay? It's really important to note that. Good, okay, so right now we know how does each piece look like. What do I mean? We know that EB is actually equal to the integral of dEz. Yeah, let's not do a vector, we know it's only in the z direction. Magnitude is going to be enough for us. So this is equal to, we have this term over there, this one equal to dE, integral of dE, multiplied by sinus of phi, and we know that this one and this one is h over d, this one is k sigma, right? P0, sorry, not sigma, we already put sigma, P0 r squared, right? Multiply by the area, which is dr r d theta, right? Divided by d, right? D squared, right? And I know that, oh, I have this thing here and this thing here, which means I have two things that I need to look at when I sum up the contribution of charge. I need to note that the radius is where? From the middle of the flower until the end. Good. And what is the angle? I have one flower or I have many? I have one. I start from 0 and I'm going to end up in the radians 2 pi. whole cycle, finish the flower, right? Good. So we need to solve that. This is a constant. This is a constant. I can drag them out, right? There's nothing that depends on theta here, you see? So I can also write 2 pi outside. Good. And I want you to be super duper careful. D cannot go outside of the integral. Why? It's built from R. And there's integral on R. Understood? Good. So we have here R to the third divided by D to the third. And this is, guys, a really nasty integral. Okay? So there's a way to solve it, okay? You need to work it out. And one of the things in this chapter is actually solving some integrals. And but I'm going to give you the final result of it, okay? The final result of this integral is actually, this is a constant, right? This is just a constant. I'm missing something, this, and h, right? We have also h. H can go outside. It's not relevant to the question. Good. So this is an integral, and the result is drums is, let's call it c, just a constant, right? Not to write a lot. And here we have r to the square plus 2h to the square divided by r squared plus h minus 2h. This is the result. Got it? So this is kind of a, what is this? Is a function, right? It's a function of what? The size of the flower and how much high I am from the flower. What is my altitude? Understood? Okay. Last question I want to ask you. Okay? Not all the flowers are the same. Okay? So let's say that the flower have right now only charge at the outer part, not in the middle. Okay, for example, this is going to be r over 2 and this is going to be r. Got it? Symmetry still holds, right? Okay, for every charge here I have the other charge over there which cancel out perfectly. I know it's going to be only in that direction. Good. But what's going to be the magnitude right now? This is a classic question for exam. Okay? Change something small in the exercise that you saw and ask you a question to see if you really understand it. So what's going to be the answer right now? Let's do E star. What do you suggest me to do? Great. You're taking what we talked before. If we're going to change the integral boundaries, this is going to be updated to r over 2, and I'm going to solve again the integral, right? So, more easy thing you can do is use the superposition. Okay, think about it. That if I have a flower, okay, that produce this electric field, this our solution, and if I'm going to add to the world a small flower, right, in this radius, r over 2, with this amount of charge, the solution would be a charge that don't have anything here. You see it? If I'm going to add this to the world. So I actually can take my results already and say, okay, dude, it's just that thing, right? It's C, F, R, H, right? Minus, the minus came from the charge. I put here a minus charge right now. Minus C, F, R over 2. It's a smaller flower with the same height. Okay? And you're done. You solve the question. So this is the concept of the superposition. And you see that all over the class, okay? Every time you see a really scary question, oh my God, what's I going to do with that and stuff like that, the only thing you need to ask, wait a minute, do I see the superposition principle here? That's going to help me. Okay, guys, we finished for today, and I want to tell you what we're going to do next. This method that we did today, you're going to see it in the homework, believe me, it's really hard. It's a really complicated and nasty way to calculate things. It's important, sometimes there's no other way around it. But the next subject, it's a genius subject, which say, if I see symmetry, really nice symmetry, like we had here, I can solve the problem immediately, okay? So the next tool we're gonna have, it's a tool that actually gonna save us from that. This is really important. That's gonna be in the exam, because sometimes you cannot go around it, okay? Sometimes life is hard. Engineers, you know that, okay? But sometimes you have another way to do it. Okay, guys? Thank you so much for today. See you next week.